we are going to look at the aldol condensation of an aldehyde. So what you would start out with is, of course, an aldehyde. You can do this with a ketone. I'm just going to show it with an aldehyde. Be aware, though, if you are starting with a ketone, you may be operating under kinetic or thermodynamic control, and there may be more than one product if it's an asymmetrical ketone. But I'm just using an aldehyde so that there is only one alpha carbon with alpha protons. So the proton coming off of the carbonyl carbon directly, that is not the alpha proton since it's not attached to an alpha carbon. The conditions for the aldol condensation would be such that you have hydroxide present and it will be kept cold. So the conditions here usually are something like potassium or sodium hydroxide in water, and you keep the conditions cold. Okay, these are the typical conditions. Now, hopefully you remember from class that these alpha protons, I'm going to circle them in green here, are semi-acidic. It's not that they're extremely acidic. They are on an sp3 hybridized carbon, but they are more acidic than your typical proton on an sp3 hybridized carbon. These would have pKa's somewhere around 16 to 20, depending on whether they're on an aldehyde or a ketone. And those on an aldehyde typically would have pKa's around 16 to 17, and those on a ketone would be maybe 18, 19, or 20. Hydroxide is not a strong base in this case. This is going to form more of an equilibrium reaction because by removing one of these protons, you don't make a weaker acid-base pair. It's probably more of an equivalent acid-base pair. But this will have the ability to do an equilibrium reaction as you remove this proton. So this base here is strong enough to come up here, take the proton, and as you take one of these protons, you would break the carbon-hydrogen bond, and carbon being more electronegative, carbon will take those electrons. And again, this is an equilibrium reaction. What you produce by doing so is water and the corresponding enolate. Now, enolates have resonance structures. I'm going to draw out all of the bonds to this alpha carbon so that you can see where everything is. That lone pair of electrons on that carbon can be delocalized through resonance onto the oxygen. Now, as you look at both of these resonance structures, the one there on the right is actually the predominant resonance structure. But I like to look at the one on the left because it's more useful to me personally as I look at the mechanism. But be aware that there is resonance and that the one on the right is the predominant resonance structure. Both of these resonance structures, everybody's got an octet. There's always a negative charge, but oxygen is the more electronegative atom. So when the negative charge is on the oxygen, that is the predominant resonance structure. Well, at this point you would have two different bases in solution. You have the enolate, and again I'm going to draw that in the two different forms. This is again the predominant resonance structure. This is the one. Now there's still hydroxide in solution, and hydroxide may actually act as the nucleophile toward the aldehyde or ketone, but by doing so you'd only make a hydrate and it would have to fall apart for chemistry to occur. So we're not going to show any chemistry where the hydroxide is adding to the carbonyl carbon, even though that is an option. It just makes a hydrate that would dissociate again. Now you can use either of these two resonance structures to show nucleophilic attack at the carbonyl carbon of the aldehyde. If you're using the one that I find the easiest to use, which is the less predominant resonance structure, you add the carbon directly to the carbonyl carbon and break the carbon-oxygen pi bond. If, on the other hand, you want to use the other resonance structure, the predominant resonance structure, you need to have the carbon-oxygen bond reform, then take the electrons in the pi bond and add them to the carbonyl-carbon and break the pi bond to the oxygen. You can get to the same place by using either resonance structure. And when you've done so, oops, wrong color. You're going to have the corresponding conjugate base of an alkoxide, so you still have not increased the basicity any. I'm going to draw out these other pieces that were here for a moment. Okay, so this piece here on the top, this came from the enolate, and this piece here on the bottom came from the aldehyde that it was added to. So let me go back a moment so you can see these pieces. This was the piece that we added to, and these others were the piece, you can use either one, that was added. Okay, so if you're having a hard time knowing what came from where, I hope that helps a little bit with some color. So you get this intermediate, okay, and it's kind of an alkoxide. Now, water is also present in the solution. We saw that earlier, being formed. And you now use the water as a proton source, so you can use this oxygen to pick up the proton and give electrons back. By doing so, you get to your final product. Oops, I don't think I drew that part right. Sorry. Let me fix it. Okay, so this is where you're going to get to. And they call this an aldol because it has an aldehyde functionality and an alcohol functionality. That's why it's called aldol. And they are always going to be beta to each other. If you were looking at this, is the carbon of interest, here is alpha, and here is beta in relation to that. So they will always be beta to each other, these two functional groups that you are adding. Now, that's what you get when you are in cold conditions. If, on the other hand, you heat this up, there will be a second step that you can go through. So this is where you're going to stay if it's cold. But if, on the other hand, your conditions were KOH, water, and heat, you do everything that I have shown you previously. All of that occurs, and you make this aldol product. But it doesn't stop here. It will continue on. And what's going to happen is you still have hydroxide in the solution here. And this hydroxide is going to remove the proton on the alpha carbon to both of these groups. So it will come in here and remove this particular proton, and you'll give electrons back to the alpha carbon. And this will make a new enolate. Okay, now this enolate has resonance delocalization of the negative charge through the carbonyl oxygen. So I want to show that. And I also want to show you what happens as it rearranges. But let me first off draw you the resonance structure. Alright, water's in the way. I'm going to erase it here for a second. Okay, we'll just redraw the water here because that was in my way. Okay, so these would be the two resonance structures that we're dealing with. And again, the one on the right is the predominant resonance structure, but the one on the left I find is easier to work with, and it will be more understandable as to what happens in this next step. This next step is the slow step, and you can do this from either of these two resonance structures, but this enolate rearranges, so you can have the negatively charged oxygen reform the carbon-oxygen double bond. This pi bond makes a carbon-carbon double bond here, and you actually kick out hydroxide. Now, hydroxide is not normally a good leaving group, but you're already in base, and you're not creating a stronger base by doing so, so this is acceptable. You could also do it from the resonance structure here on the left. Just take this pair of electrons, make the pi bond, and kick out your hydroxide. So you can do that from either one of those two resonance structures. I'm trying to draw things in the same locations so that you can keep track of what was where. And again, we've regenerated the base, but we have not made a weaker acid-base pair. What we've made here, though, by doing this, is an alpha-beta unsaturated aldehyde, or to make an alpha-beta unsaturated ketone. And these are neat because they're part of a conjugated pi system. You have alternating double, single, double bond right here. So you've made a conjugated pi system. And when you heat something up, you're trying to make something more stable. And if you can get a conjugated pi system where you didn't have one before, this is a good thing. And this is why we would take the time to do this.